Hello, and this time, welcome to Norton's theorem. Norton's theorem is very similar to Thevenin's theorem, except that it doesn't use a series resistor and a voltage source in the equivalent network. It uses a current source and a parallel resistor. Apart from that, the two theorems are pretty much the same. They both apply to any linear two-terminal network and say that you can replace any such network with a much simpler equivalent network consisting of one independent source and one resistor. That just leaves the problem of how to work out the current source and the parallel resistor for a Norton equivalent circuit. And we can proceed pretty much as we did for the Thevenin equivalent networks. We can consider the open circuit voltage and the short circuit current. If you have a Norton equivalent network and you consider the open circuit voltage, that's the voltage that would appear across the terminals when there is nothing connected across the terminals, then all of this current here would be flowing down through the parallel resistor here. So the voltage generated across this parallel resistor would just be the current times the resistance. It's just Ohm's law again. The open circuit voltage would be the Norton equivalent current multiplied by the Norton equivalent resistor. And we can consider the short circuit current as well. If we connect a short circuit between A and B, connect them together with a wire, then we have a current divider. But this current divider has a 0 ohm resistor between A and B, which means that all of this current is going to flow out between A and B, and none of it is going to flow down through that resistor. So the short circuit current is just the Norton equivalent current. You'll notice that in this case, the Norton equivalent resistance is equal to the open circuit voltage divided by the Norton equivalent current, which is itself equal to the short circuit current. So that's the open circuit voltage divided by the short circuit current. And that's exactly the same formula that we got for the Thevenin equivalent resistance as well, which gives us the useful result that the resistance in the Norton equivalent network is equal to the resistance in the Thevenin equivalent network. The current in the Norton equivalent network is just equal to the short circuit current. Let's do an example of working these out for a real circuit. First, we'll work out what the open circuit voltage is. And we can do that using superposition. As we've done before, it's usually the easiest way to do this. Superposition, firstly, will turn the current source on, but leave the voltage source off. If we leave the voltage source off, then we're effectively replacing the voltage source with a 0 volt voltage source. In other words, it's a wire. So we would end up with this circuit here, and we want to know what the voltage between A and B is. Note that we've now got a wire connecting from here to here, so this point here and this point here would be at the same voltage. There is no current flowing through the 1K resistor, so there's no difference between the voltage at this point here and this point here either. So with no voltage between here and here, or between here and here, the voltage between A and B is just 0. First contribution to our open circuit voltage is just 0. Next, we'll consider the contribution of the voltage source. This time we turn the current source to 0, which means replacing it with an open circuit, which is just nothing. Now we have a 2 volt voltage source between here and here. no current flowing through the 1K resistor because there's nothing connected between A and B. There's nowhere for the current to flow. If there's no current through the 1K resistor, there will be no voltage across it. So the voltage here would be the same as the voltage here. In other words, the voltage between A and B is just the same as the voltage across the voltage source between there and there. It's just 2 volts. So the total open circuit voltage that we have is just 2 plus 0, 2 volts. We could go on to derive the short circuit current in the same way, using linearity and superposition, but it's easier to use the shortcut and go directly to the equivalent resistance. And the shortcut is to turn all of the sources to 0. If you turn all of the sources to 0, then you just end up with this. A 1K resistor going through a wire, which is the replacement for the voltage source, and a 2K resistor in parallel with the wire. What is the total resistance between A and B? Answer: 1K in series with the parallel combination of 2K and a wire. Well, anything in parallel with a 0 ohm resistor is just 0 ohms, so that's just going to be 1K. So our Norton equivalent resistance is just going to be 1K. Now we know that the short circuit current is equal to the open circuit voltage divided by the equivalent resistance. So our short circuit current in this case would be 2 divided by 1K, or 2 milliamps. So our Norton equivalent network would be a current source of 2 milliamps in parallel with a resistor of 1K. Does it work? Once again, we can check using the simulator. I've built up the network and the Norton equivalent network here, and put an identical diode as a load to both of the networks, and yes, we're getting the same voltage and the same current in both cases. And this would be true no matter what the load was here. I could replace this with a resistor and it would still be the same. Let's have a go at doing that. Yep, again, same voltage, same current. So that's Norton's theorem. Exactly the same idea as Thevenin's theorem, and it applies under the same circumstances for a 2-terminal linear network. It's just that the equivalent network that it produces is different. It's a current source in parallel with a resistor, rather than a voltage source in series with a resistor. One useful thing is that once you know the Norton equivalent network, or the Thevenin equivalent network, it's really easy to convert one to the other. And we'll see that that is the basis of a circuit analysis technique called source transformation that we'll be looking at in a few videos' time. Next time, we'll have a look at a few special cases which can speed up the analysis and the derivation of these equivalent networks.